Welcome back, everyone. We're now in topic 7, which is going to cover molecular geometry and covalent bonding themes. Let's think about where we've been in the past few topics. In topic 5, we started to learn about compounds. We started to learn how to name and write them. In topic 6, we took that a little further and started to learn how we can actually represent bonding with what we call Lewis dot structures. In topic 7, we're now going to take it a little further still, and we're going to be looking at what are the shapes of molecules. The shapes of molecules may not sound exciting, but it's actually extremely important when it comes to how fast reactions happen, when it comes to what type of molecule will react versus another, and many other things. In fact, molecular shapes are what drives the pharmaceutical industry and how we design drugs. So in this topic, we're going to get an introduction to all of the bonding theories and the molecular geometry theories that are used. Starting off with section 1, which covers Vesper Theory and electron domain geometry. So what is molecular geometry? As you've probably already guessed, molecular geometry is simply the shapes of molecules. You see, molecular geometry is going to affect how molecules bond in reactions. Molecules also you're going to see have bond angles, which affects how they react and how quickly they react. What actually creates the shape of the molecule, though? Well, it's the idea that there are these areas of the molecule where electrons exist. And since electrons are going to repel from other electrons, the result of the repulsion is what creates the shape. This is known as Vesper theory, or we could say valence shell electron pair repulsion. Like I said, the valence electrons are what are involved in bonding, and when those valence electrons begin to repel from one another, that's where you end up getting resulting shapes. For example, we have in this slide here a few images of some molecules that have different types of shapes. For example, we have linear shapes, we have trigonal planar shapes, as we'll learn later. We even have shapes that kind of look like pyramids. We have lots of different shapes, and so what we're going to learn in this topic is how you can predict what kind of shape is going to be there. Before we get started, it probably is a good idea, if you haven't done so already, to print out or have ready the molecular geometry sheet that is located in the additional course materials in Canvas. I'll also be showing you some cheat sheets in these videos, but it's probably a good idea to have that out as well, so that way you can take notes on that. Alright, so we're going to be talking about electron domain geometry, but before we can talk about what electron domain geometry is, we need to first understand what an electron domain is. So remember, a pair of electrons can come in two forms. They could actually be bonded, which means they're between two atoms, or they could be lone pairs, which means that they're not bonded. Remember that bonding can be single bonds, double bonds, or triple bonds. So, what's an electron domain? An electron domain is a region of space that an electron occupies. Electron domains can either be lone pairs, or they can be a bond. In terms of a bond, we're going to count single bonds, double bonds, and triple bonds all the same. All of them will represent just one electron domain. So let's take a look at example 1. All we have to do in this example is identify how many electron domains there are. Now when we talk about geometry, it's only the electron domains that are around the central atom that are important. That's it. So remember, what's an electron domain? An electron domain is either a lone pair or it's a bond. And remember, a bond, single bonds, double bonds, and triple bonds will all count as just one. And so if we take a look at water, how many electron domains are there in this molecule? Well, there's 2 lone pairs, and then there's 2 bonds. So total, there are 4 electron domains. Let's take a look at the next molecule, XeF2. Remember, we only care about the central atom. So if I take a look at xenon, I see that there's 3 lone pairs, and there's 2 bonds. So total, there are 5 electron domains. Let's jump down here to HCN. Looking at carbon, we have 1 lone pair, and we have 2 bonds. Doesn't matter that it's a double bond, we count that as just 1. So in this molecule, there are 3 electron domains. Next, we look at SO3. Around the sulfur, we have a lone pair, and then we have 3 bonds. So there are 4 electron domains there. And then finally, we have PCl5. There are 5 bonds and no lone pairs on the central. And so in this one, there are 5 electron domains. Pretty simple, right? Pretty straightforward. So now how are we going to use that information? Well, remember, what's an electron domain? An electron domain is a region of space that electrons occupy, and electrons want to repel from one another. So, depending on how many electron domains there are, will dictate what the electron domain geometry is. So the electron domain geometry I like to call, it's the skeleton shape of the molecule. Essentially, it's just showing you the different regions of space that electrons can occupy. And those electrons can either be bonds or they can be lone pairs, and we'll see examples of this. There are 5 electron domains. Now, real quickly, what's difficult in this topic for students is it's very visual. So I try to put as many visual helpful tips in the topic so that way it can help you. However, if anything is not helping you, feel free to Google or YouTube electron domain geometry or molecular geometry, and there's a lot of resources out there. Okay, with that being said, let's go through the 5 electron domain geometries. So the first one is when you have 2 electron domains, or 2 regions of high electron density. When this happens, you end up having your central atom having 2 electron domains around it. If you think about that, the furthest those electron domains can get away from each other is when they form 180 degrees. In other words, it creates a linear shape. So that's as far away as they can get from each other. When you have 3 electron domains, think about your central atom here, you have 3 regions of space where electrons can occupy. The furthest those electrons can get away from each other is where you have a 120 degree angle. This is known as trigonal planar. Notice that word, trigonal, meaning 3, and planar, meaning it's flat. It's in the plane of the piece of paper or plane of the board. All right, the remaining 3 is where we really start to get some 3-dimensionality. If you have 4 electron domains, that means you have 4 regions of space around the central atom that electrons exist. This is going to give way to the bond angle of 109.5 degrees, and this will produce the tetrahedral. You might have heard of the game Tetris, which is where the word tetra prefix comes from, which means 4. If you have 5 electron domains, that means there's 5 regions of space surrounding the central atom. With this, you actually have 2 bond angles. One of the bond angles is going to be 120 degrees. That's going to be, and let me get rid of some highlights here so we can see it. That's going to be between these 3 regions of space in the equatorial position. I'll talk about that later. And then you also have a 90 degree angle between the axial positions. When this happens, you get what's called a trigonal bipyramidal shape. And then finally, when you have 6 electron domains, you have 6 regions of space surrounding the central atom. The bond angle for that is always 90 degrees, and that's going to produce an electron domain geometry, what we call octahedral. Now you may be wondering, why do they call it octahedral when there's only 6 electron domains? Wouldn't that be, doesn't octa mean 8? Well, it's octahedral, which means if you were to think of 4 strings going up to the top like this, and then 4 strings going down to the bottom like that, you would end up creating this geometric crystal that would have 8 sides, which is why they call it octahedral. So that's why they call it that. Like I said, this is a very visual topic, so we're going to see a lot of pictures to help you out with this. So let's actually start looking at that. Okay. Real quickly, this is another chart that kind of shows exactly what I went through. Notice the first 2, the linear and the trigonal planar. Notice how they're flat, right? Those molecules are going to be, flat. So you have your linear and then your trigonal planar, which I like to call the trigonal planar. Kind of looks like the Mercedes-Benz symbol, but it's flat. It's the other 3, the tetrahedral, the trigonal bipyramidal, and the octahedral. These are the ones that actually are more 3-dimensional. And you have those pictures over here to the side. Like I said, I'm a visual person, and that's what helps me with things like this. So let's go ahead and actually look at a website. In your printable notes, your student fill-in notes, as well as here, there's actually a website that you can just click the link to. And I'm going to do that right now. So I'll see you on that web page. Alright, so I'm on the web page now, and what I did is when I clicked the link and I ran the simulation, I clicked model. You can also use real molecules too, but the model will work just fine. So when you open it up, you actually end up having bonds that are already there. I went ahead and got rid of them. So the purple atom that you see here represents our central atom. What I can do is I can add on single bonds, double bonds, and triple bonds, as well as lone pairs. And the really cool thing is when we start adding certain bonds, we can see not only the molecular geometry, which we haven't learned yet, we'll learn in another video, but also the electron domain geometry, or sometimes just we say the electron geometry. And you can also show bond angles too. So there's a lot of cool options. Okay, so let's go ahead and start looking at the visual. If I add in two bonds, do you see how to get as far away from each other as possible, they have to be 180 degrees. If I were to click and drag this and try to get closer to that other one, do you see how that other one tries to get away from it? Because remember, electrons want to repel from each other. So according to the repulsion, this is as far away from each other as they can go. Notice the 180 degree bond angle, which that is linear. I'm not going to show molecular geometry because we haven't learned that yet. So we're just going to focus on linear. You may be asking, what's the difference? We'll talk about that later. Well, what happens when we add in 3 electron domains? You see there, this is where we have the trigonal planar shape. But you can see why I also like to call it the Mercedes-Benz symbol, right? You can see that we have those bond angles of 120 degrees, and the trigonal planar is the name of the shape. Now, if I were to pull this like this so we can see it on its side, you notice how it's planar, right? It's flat. So those are our first two. Now, what happens when we have 4 electron domains? When you have 4 regions of space around the central, notice the shape. It's not going to be something like this, like a T shape. It actually looks like this, which is known as the tetrahedral shape. I like to call this the ceiling fan, because think about it. This would be like the pole that goes up in the ceiling, and then here are your blades. What's important to know that it actually doesn't matter which way or which atom I make on top. Does it actually change the shape? No, it doesn't. The farthest repulsion that these electron domains can get from each other is 109.5 degrees. And once again, that's known as the tetrahedral. If I add in 5 electron domains, this is where we get the name trigonal bipyramidal. Now, this is probably the hardest one, I think, for students to visualize. So here's a trick. Imagine you take linear and trigonal planar and form them together. So your linear, as I have it drawn here, your linear is what's going up and down. So you've got your linear right here. And then your trigonal planar is what's right here in the side view. So this side view is what we call equatorial. So think like equator. And then axial is the up and down position. So notice the bond angle, let me turn it to the side, is 90 degrees between this atom in the axial position and these atoms in the equatorial position. But if I were to turn it on its side, so we can see along the linear path, now you can see that's where the 120 degrees is, and that's the trigonal planar part. But like I said, together, this molecule is what's known as the trigonal bipyramidal. Oop, let me turn it up. There we go. And then finally, if we add our 6th electron domain, this is going to be your octahedral. Okay, and your octahedral has those 6 electron domains. That is 90 degrees. It doesn't matter what atom I make on top. It's always going to have the same shape, right? So that's going to be the different shapes. And like I said, this website's really good for visualizing that. So welcome back to the PowerPoint. So what I have here is your 5 electron domains, or 5 electron domain geometries. So we have 2 electron domains, which is linear, 3 electron domains, which is trigonal planar, 4 electron domains, which is tetrahedral, 5 electron domains, which is trigonal bipyramidal, and 6 electron domains, which is octahedral. So I have those there. Sometimes you might be asked to draw those on paper. And it's like, well, how do you draw them on paper when they have 3-dimensionality? Well, the first 2 are easy, right? Drawing something linear or drawing something trigonal planar is pretty easy because they are flat by nature. But how do you draw on paper something that is 3-dimensional, such as tetrahedral? You notice that we have what's called the line, dash, and wedge notation. The line, anytime you see a line, that's going to represent bonds that are in the plane of the paper. Okay, it's flat in the paper. Anytime you see the wedge, that's an atom that is sticking out of the paper. And then anytime you see a dash, that's going behind the paper. So you can imagine, okay, that's how we would draw those 3-dimensionality structures on a piece of paper. So that wraps up electron domain geometry. I'll see you in the next section where we start to talk about molecular geometry.